Now, in order to understand what's really happening inside of an atom, what specifically is the electron doing in there, we need to have some way to probe atomic structure. And one way to do that is to look at electromagnetic radiation. Atoms will emit an electromagnetic radiation, and sometimes they'll absorb it. And if we look at the properties of that radiation, those are valuable clues about what's happening inside the atom. In order to understand that, we're going to need to know what electromagnetic radiation actually is, how you create it, what its properties are, how it behaves. So that's what we're going to do in this lesson. We're going to look at electromagnetic radiation and see what its properties are and how those properties are related to each other. Now, on a large scale, electromagnetic radiation acts like a wave. And you know what a wave is. But let's look at waves as a way to move energy from one object to another. Let's suppose you're in a swimming pool, and here's the surface of the swimming pool, and over here, maybe you've got a little duck or something. And over here, you are gonna maybe do a cannonball into the water. Now, what's going to happen? You're going to get a wave that's going to propagate out from the point of disturbance here towards the duck. And there'll be a ripple one instant, the next instant after the impact. You know, you're going to be maybe down here. You'll pull the water surface down and it'll bunch up there a little bit. And you're going to make a sort of a pulse. This dotted line is where the natural water level would be. And that pulse is going to move over here. It's going to propagate over. Towards the duck. And then the next instant it might look like this. Let me move the water level down here a little bit. So here's that pulse hitting the duck. There'll be a little trough there. Maybe this would be the natural water level, where the natural water level would be. So this is the pulse that you made, the wave that you made by jumping into the water. Now what's happening here is that the duck is being lifted by that distance. Now the duck has some weight, so you're lifting a weight there. So you're doing some work. Work is being done. And what is work anyway? It is pushing an object, in this case the duck, against an opposing force. So you're doing some work. Where did the work come from? How do you do the work? Well, you need to expend some energy. Energy is the ability to do work. Energy, like matter, isn't created or destroyed. So energy has to come from somewhere. If I am lifting this duck up, I'm doing some work, and that means that I'm spending some energy. So something had to lose energy in order for the duck to get it. The duck is gaining energy here, and something else is losing energy. Now, what's losing energy? It was the source of the disturbance. So energy is lost here. And energy is gained here, where you're receiving. So what it amounts to is that you're taking some of the energy that you had when you did the cannonball, and you're moving it through space over here, and you're spending it. You're giving it to the duck. You can't create or destroy energy. You can only move it from one place to another. And this wave is the means that moves it from one place to another. So this is the big idea here in this video, that a wave can be used to transfer energy from one place to another. Now, there's a couple kinds of waves that you can have. This wave here moved through space, the wave that we're talking about. So this is a traveling wave. A traveling wave, it's kind of obvious what it is. You can see the peaks moving. The whole wave actually moves. It's a pulse wave. There is pretty much just one disturbance. So there is there's a lead peak and it kind of dies off after that. So a pulse might look like this. Let me exaggerate it a little bit. So here you have like a little wave coming, and it's a pulse, just a pulse coming through. Now, you can have a continuous wave. So suppose you had been bouncing up and down, both ways. So you're going up and down like this. Then suppose this is, just for something different than a water wave, an electron. And suppose you had some protons out here. And over here I have another electron. Suppose I'm going to do a continuous wave, and that is one where I just keep on bouncing up and down. So there's not just one disturbance like in a pulse wave. There is an oscillation, let's call it. That's where an up and down kind of motion here. Could also be a back and forth kind of motion, but the important point is that it repeats. Now, back to this. Suppose we've got an electron that we're oscillating. We're moving up and down like this. What's going to happen to all the protons? Well, positive attracts negative, right? There's an electric field that is around this that can actually be seen by these other protons. So positive attracts negative. If it moves down, this one's going to want to move down. And this one too. But there's kind of a lag. If I'm moving up and down, there's a little bit of a lag between when each of these protons sees the electron. And maybe this one is stationary, and this one is seeing it when it was up like that. And then this one is seeing it when it was down and down. And now if this one moves down, this is going to move down. So this is moving with that one. Alright, if you look at this, it's kind of like a water wave. It's not too different. If you draw an envelope on the outside of these little arrows that show which way the positive charges are being tugged, it really does look like a wave. And it's going to be a continuous wave. If I draw it like in a little bit more detail, it's going to look like actually a sine wave, and mathematically it is a sine wave. You just keep on bouncing that charge up and down. You get a wave that looks like this. It's going to be tugging all of these things, so it's doing some work. So this electron in your transmitter is losing energy because it's doing work on all of these things. And this over here, this electron, you can say is a receiver. It's gaining energy. And notice that when you have an up and down motion over here, it's with a little bit of a lag, it's appearing over here at the receiver. So you're not just transmitting energy from one place to another, you're transmitting information. So you can broadcast a radio signal or a TV signal or whatever using this scheme, using this wave. So there's a little simulation that you can see linked below this video where you're wagging a charge in an antenna at a radio station up and down, and you're looking at this electric field wave that is rippling out from it and hitting a receiving antenna over here. And you can play around with that a little bit. You can do it as a pulse where you're just manually like moving this electron around and seeing what it does to this electron over here. Or you can do it as a continuous oscillation. It just keeps on bouncing up and down and up and down. And you can see that this one will start wagging up and down in sync with this one over here. Either way, you have to have some power here to keep this moving up and down. You have to have some energy. This is why you have to charge your cell phone. Your cell phone, it takes some work for your cell phone to keep on wagging that up and down. Your cell phone is broadcasting energy out. So you have to replace it somehow. So the charge on the cell phone runs down. All right, so types of waves. You can have a pulse wave, which is one disturbance, and you can have a continuous wave, which is a sort of an oscillation, an up and down kind of disturbance. You can have a traveling wave, as one that moves from one spot to another. But there is another kind of wave that I want to tell you about, and that is a standing wave. Suppose you pluck a guitar string. So here's a guitar string. It's held down on either end here. And you grab it right there and you pull it up and then you let it go. So this would be kind of a pulse wave, right? One disturbance. But the thing is, the guitar string will move up, and then the next instant it'll be moving down, and it'll kind of twang back and forth between these two positions. It'll move up and down like this. You've got a wave there. It's an up and down kind of motion that you caused. But the wave, instead of being able to travel, it hits the end of the string and goes back, gets reflected back. So there's a reflection going on here, and that keeps the wave kind of trapped here. You can see this a little bit more clearly if you pluck the guitar string like this. So here's the guitar string again. And I'm going to put my finger right there. And I'm going to force that part of the guitar string not to move. So I'm like this. And then I'm going to pluck it right here. And I'm going to make a wave then when I pluck it like that looks like this. Now the guitar string has to stay attached at the ends here. But I forced it to have no, we call it amplitude, no movement away from the bass line here. And the next instant, at this instant, this is up, and this is down. But at the next instant, it's going to go the other way. You can draw that in as a dotted line, maybe. So it's going to go up and down like that. Up and down like that. So it's kind of like this wave hits there and then gets reflected back, and then hits there and gets reflected back. And it's trapped on the guitar string. This is called a standing wave. So a standing wave is trapped in one place. It's trapped on this guitar string in this case. So you can't say exactly where the wave is. If someone says, "Where's the wave?" and you say, "Oh, it's right there." Really, that's not right, because it's everywhere along the guitar string. So the wave itself doesn't have, like, it's located on the guitar string, and that's the best you can narrow down the one place here. So 4 types of waves. You can have pulse waves, or you can have continuous waves. You can have traveling waves, or you can have standing waves. And we're going to talk some more about that in the rest of the lesson.